Today I'm going to be showing you something about how to do what's called a Becke line test on the microscope. But before we do that, as background, we need to understand a few things about indices of refraction. So a fundamental property of all minerals is that they have an index of refraction. And as you can see, the index of refraction is defined as the velocity of light in air or a vacuum divided by the velocity of light in the mineral. And for common minerals, these values range from about 1.4 to 2. It's called an index of refraction because when light passes from one medium with a particular n into a medium with a different n, the light is bent or refracted. And if you've ever been fishing and stuck your fishing pole in the water, you've probably seen this because your fishing pole looks like it's bent. In the late 1800s, an Austrian mineralogist named Friedrich Becke devised a method for comparing the relative indices of refraction of two materials. In our case, the two materials could be a mineral mounted in epoxy, or it could be a mineral immersed in a refractive index oil with a particular value, or it could be two adjacent minerals. The contrast in indices of refraction cause the light to be bent, but the direction of bending or refraction varies depending on the relative indices of refraction of the two materials. This diagram illustrates the concept. So here we have two minerals, fluorite on the left and grossular on the right, mounted in a refractive index liquid that has an index of 1.51. Fluorite has a refractive index that's less than that of the liquid, and grossular has a refractive index that's greater than the liquid. As light passes through the fluorite, which has an index of refraction less than the liquid, the light rays are bent away from the fluorite, and the opposite is true for grossular. The light rays are bent toward the grossular. What Becke noticed is that if you increase the distance between your eye and whatever you're observing, in this case the minerals, a bright halo or line will move into the material with a higher index of refraction. This bright line or halo is known as the Becke line, named for its discoverer.
All right, so now that you know a little bit about the history of the Becke line, where the name comes from, and what it's designed to do, I'm going to show you now how the Becke line test works. So as you see there, in this field of view, there are several grains, in this case mounted on a glass slide in an epoxy, and it happens to be manufactured by a company named Buehler, and the index of refraction of the epoxy is about 1.53. So using the Becke line test, we can determine whether the mineral's index of refraction is higher or lower than that of the epoxy. So we're getting a relative indication of index of refraction. So the test works best at the highest power objective, which on this microscope is a 50x objective. So I'm going to swing that into the path of light. And this is an edge phenomenon, so we're going to cut down on the light a little bit using a diaphragm under the stage, which enhances edge effects. Now the way to do the test is to lower the stage, increasing the distance between your eye and whatever you're looking at. And you will see when I do this a halo form. In this case it's going to move out of the mineral into the epoxy as I lower the stage. And the principle here is that the halo moves into the substance with the higher index of refraction. So in this case, the epoxy, which has an index of refraction of 1.53, is higher than the mineral's index of refraction, which must be essentially something less than 1.53. So we can't quantify that, but in a qualitative way, we can say that. And that may or may not be an aid to identification if you have an unknown mineral that you're looking at.
All right, so now you know how to do a Becke line test. And as a point of interest, you can use a Becke line test to pinpoint the index of refraction of a mineral. Let's say, for example, you had an unknown mineral that you were trying to identify. You could immerse it in a series of refractive index oils that have different indices of refraction. And what you're looking for is a match between the index of refraction of the mineral and that of the index oil. And as you get closer and closer to that match, the edges of the mineral grain will get fainter and fainter and fainter. And theoretically, if you have a perfect match between the index of refraction of the mineral and the index of refraction of the oil, the mineral would effectively disappear. And that's pretty cool.